G'day viewers. In this segment we'll talk about Dijkstras' algorithm for computing shortest paths. This will let computers do the calculations instead of us, which is generally a good thing. So the figure down below here shows an example of a network topology. What we'd like to be able to compute in this network topology is the source tree from a particular node, like for instance E, out to all of the other destination nodes in the network, all of the other nodes as destinations. This will allow us to work out the forwarding table for E, or which way to go to reach all the different destinations. If we can do that, we've solved the forwarding problem. Dijkstras' algorithm provides one way of computing these source trees, and it's widely used as part of a common routing protocol, which is why we're covering it. Dijkstras' algorithm is named after E.W. Dijkstra, a famous computer scientist. He is well known for his contributions to programming languages. You might have heard of a paper called Go To Considered Harmful. That was him. He's also made many contributions to distributed algorithms, such as the algorithm we'll study for computing shortest paths, as well as program verification. So Dijkstra's algorithm that we'll look at, it dates from 1969, so it's been around for a while. It's a single source shortest paths algorithm, which means that it takes a given source, and from that source it computes shortest paths to all of the other nodes in the network. To do this, it needs to know the network topology, and there's also a caveat, a little restriction here. All of the link costs that are on the various links in the network need to be non-negative. This is usually perfectly fine for using network graphs, because if the quantities, the costs, correspond to anything physical or meaningful, chances are that they're non-negative anyhow. Okay, so here's an outline of the algorithm. I'll go through this outline and then we'll work through an example so you can see it in action. So first of all is an initialization step. Dijkstra's algorithm is going to visit all of the nodes. So we begin by marking all of the nodes as tentative, and we set up distances for them. All of the nodes are keyed by their distance. The distance of the source from which we want to compute the shortest paths from there out to everywhere else is set at 0. And the distance of all of the other nodes, we'll initialize it to be some constant that means infinity. We don't know how to reach them yet. And then we proceed in this main loop. This main loop says, while there are any nodes which are tentative, meaning the algorithm hasn't found them yet, how they fit in to the source tree, then what we will do is we'll extract the node with the lowest distance that we know. We'll then add that node to the source tree by drawing a link from wherever it was used to get its current distance to the node. And then we will use the information from that node to relax other costs, to lower other costs. We do that by taking the cost of the node, looking at the node's neighbors, and seeing if there is a lower distance way to reach any of the node's neighbors. That might sound a little mysterious, but let me go through an example and you'll see that this relaxation step is quite straightforward. Okay, here's an example that I'm going to walk through. It's the same topology from before, and I've shown it with an initialization phase where you can see that next to all of the nodes I've written in red their costs. For many nodes it's infinity. For the source node where we're going to start from, it's 0. Now I'll proceed through that while loop. First step of the while loop, we're going to take the node with the lowest distance, that's A, where we want to start from, and do a relaxation around A. So if A now has cost 0, you can see I've changed the cost to blue. It's locked in. It's once we visited the node then and taken it, then we found the path to that node. Of course, this is just the source. Now I'm going to color nodes that we visit black. And then the relaxation from here, it looks at the cost of this node at 0, visits all of its neighbors, and sees if it can lower the cost. What are its neighbors of A? One is B. You can see here I've circled B. B's cost used to be infinity, but B is one link of cost 4 away from A, which has cost 0. Therefore B's cost could be reached via A at cost 4. That's less than infinity, so we're going to lower the cost of B from infinity to 4. That's one relaxation. We'll do the same thing for E. E's cost used to be infinity when we didn't know how to get there, but now we have an option. We can go from A to E directly over this link of cost 10, so E's cost will be 10. Both of these nodes have been relaxed. That's a step in the right direction. Next iteration, what do? We pick the next lowest node. That's going to be B with cost 4, just circled B. So we add B to the shortest path tree from the source tree from A. Now B with cost 4 was reached from A directly over this link, so we add this link to the shortest path tree. Now let's perform a relaxation. We'll go around all of the nodes connected to B and see if we can use the links from B to lower the cost. Let's look at C first. C's cost used to be infinity, but C is a link of cost 2 away from B at cost 4, so C can go down to cost 6. It got lowered. E, well, E is a link of cost 4 away from B, so that can be reached at 8. E's cost before used to be 10, so actually E has now been lowered to be cost 8. So interestingly, E's distance has fallen not just from infinity down, but it used to be some finite number 10, now it's gone down to 8. So we're finding better paths over time as we go out, further and further away from A. Similarly, we'll do the relaxation for the relaxation from B when we look at its neighbor F. Its cost goes down to 7, and G goes down to 7 too. This is great. Okay, next step, what do? The next lowest cost, well, the lowest cost of the remaining nodes that haven't been visited is C with cost 6. So we take it. I've changed its cost to blue to say that it's done. We add this link. C with cost 6 could be reached at that cost from B. So we add that to the tree. That's a new link. I've colored C black too to indicate that node's visited. Now we do our relaxation around C. What's going to happen? Well, H's cost is going to fall. We have the cost of D can be reached now at 8 here. So I think D's cost has fallen too. I'm not sure. We'll see that, I guess. Well, you have to look at the previous slide. Relaxing from C, we get that the cost of E has now gone down to 7 because it can be reached over a link of cost 1 from C is 6. 1 plus 6 is 7. So it's gone down again. Wow, our route to E is just getting better and better. Yes, D, I guess D went down from, well, I don't know. You can look at the previous slide. It's hard work going through these graphs. I hope I haven't made too many mistakes that you're going to find. Okay, so continuing, well, it looks like actually we've done all of the relaxations for C. So let's continue on. Now we've got to pick the next lowest node. There are actually 3 nodes that have cost 7. So any of those will do as the minimum cost to extract. We're going to arbitrarily pick G just to work our way around the graph. G could be reached at cost 7 from B, so we've now added this link here to the shortest path tree out from A. And I've changed the cost of G in 7 to blue and marked the node G in black. Let's do the relaxation from G. G has one other neighbor. So that other neighbor we can reach at a link at cost 4. So the cost to reach F by G would be 11. 11 is not bigger than 7. So actually that means that routing to F by G would be a bad move. And we don't lower the cost. And remember that as a new route. So that hasn't changed anything. Next, moving on, we'll do a relaxation around F. So first of all, we are taking F as the next lowest node. We're going to add the link at which F was reached at cost 7 to the shortest path tree. That is a link from B. It was reached from B at cost 7. So we've added this node to the shortest path tree. We do the relaxation and we find actually that it doesn't lower anyone else's cost. Everyone else has reached a better way than going through F, I guess, is what that means. Continuing, now we get to E. So we want to do a relaxation around E. So we take E, make its cost in 7 is now in blue. We've colored the node black. We've added the link. E at cost 7 was reached via C. So we add this line from C to our shortest path tree. Now as we do that relaxation, I think nothing much changes, because by the way, all of these nodes that have already been visited and are in blue, they're not going to change. We've found the lowest cost way to reach them. The only node that could potentially change is this one in red, but 7 plus 2 is 9, that's bigger than 8, doesn't change. Okay, going on, what's left? D. D, now we'll take that as the next lowest, and we will take this link to D. We added that, relaxation doesn't change anything. And finally, there's one node left, that's H, it costs 9, so we add this one, and we're done. We've now found the source tree from A to all nodes. If you just look at all of these blue lines, you can see that they start at A, they go out, and they provide a set of paths to reach all other nodes on the graph. And these are the least cost paths to reach any of these other nodes. So we've done it. We have a nice methodical procedure for finding this source tree from a given node for a particular topology. And that's Dijkstras' algorithm. Let me make just a couple of comments before we wrap up. So you might have noticed that Dijkstras' algorithm finds the shortest paths in order of increasing distance from the source. What it's really doing is leveraging this optimality property, that for long shortest paths, the smaller shortest paths, subpaths, are also shortest paths. So we can build up from small paths to large paths, and they all overlap. And that's why it works to go out at increasing distance, and that ensures that once we've gone out to a certain distance, we'll never change our mind later and change any of the paths we've already selected. This algorithm can take a little while to run on a graph topology. Actually, the efficiency of running it depends on how you implement this extract minimum cost node function, depending on what data structure you use. You can use different ones depending on if your network is dense in edges or sparse in edges. But in any case, the running time is superlinear in the size of the network. That means as the network grows larger, the runtime of this algorithm is going to go even more quickly, and eventually, for very large networks, the runtime will get very large. It's not surprising really, there are so many different little paths that you can easily imagine some of the complexity here. And finally, I'll note that it gives us the complete source tree or sink tree, depending on which way you run it. This is actually more than we need for forwarding. Each node just needs to know the next hop for all particular destinations. So we have more than we need for forwarding. We can use it, that's great. To get this, of course, we needed to know the complete topology. So that's going to be an issue we'll have to address in routing. Okay, now that we know Dijkstras' algorithm, I think we can keep moving on and look at other routing algorithms.